Okay, so let us start with the lecture 2 and we will be continuing with lecture 3 today. Okay, so before we go into today's lecture, we haven't finished everything about the coefficients of form yesterday. So, I will just complete that. First of all, we talked about the block coefficient CB, I talked about CB, then we talked about the then there is Cm, the midship coefficient. Now, even if you do not remember the rest of it, it is very important that you remember at least the block coefficient, okay, what that expression is, and you might have to remember some value, but remember what a block coefficient is. The others are also important. The next one is midship coefficient, and there is something called prismatic coefficient. We define it by Cp. Now, Cp is defined as del, that is the volume displacement. As I have told you before, the inverted one represents the volume displacement, and the correct one, the other one represents the mass displacement or the weight displacement. Del divided by Am into L. We have already defined Am. Am is defined as a midship area. Okay. So, del divided by Am into L, this represents the prismatic coefficient. That is how it is defined. Now, as you can see, it is equal to this is just from the previous two definitions. So, this gives you. Now, as you can see, Cp does not have to be less than 1. It might be, it is a ratio of Cb to Cm, both of them are less than 1. So, it is possible that it can be greater than 1. Okay. So, then the next coefficient of form is known as a water plane coefficient, it is written as CWL. It is defined as water plane coefficient, it is given by CWL is equal to AW by L into B. Again, AW is known as the water plane area. I have already mentioned to you what is the difference between the midship area and water plane area. The midship area means you if the ship is like this, you slice it, what you get here is that area. If you slice it like this, what you get there is the water plane area. Okay. So, that is AW. AW divided by L into B. L is the length, B is the breadth. So, this will give you the water plane coefficient, that is CWL. Then the last one, last coefficient of form is defined as a vertical prismatic coefficient. CVP equals del divided by AW into T. Okay. For this exam, of course, you definitely have to remember all these values, the expressions, because I will ask you questions on that, but other than that you have to remember Cb definitely, and you have to remember these things, what is meant by sectional area, what is meant by water plane area, what is a section, what is a water plane, like that. Okay. And all those things like stations, water lines and buttock lines, all those things you have to remember. These are important things which you have to have with you all the time. The rest of it, of course, you need for the exam, for this exam. Okay. So, this is as far as coefficients of form are concerned. Now, next we can go into this week's lecture, today's lecture, that is basically about Archimedes principle. Okay. Now, some assumptions we make in this whole book, okay, or in our whole study, which does not hold really for the case of ships and ships in sea. They are: 1, water is incompressible. You might know what is meant by that. The meaning of that is, incompressible means, the meaning of it is that the density does not change. Density is fixed. Okay. you will know how a density can change, right. There are various ways in which the density can change. One of it is when the temperature changes, the density can change. And another thing which you do not see in water is in the case of aircrafts. You will see you have some aircrafts that are called supersonic, means when you go above the speed of sound, then density changes drastically. Okay, there is such a thing doesn't exist in water. There are no ships that go faster than the speed of sound, no such thing. So that doesn't hold here, but that those are some of when you are studying fluid mechanics, those are some of the things that change the density rapidly, very strongly. In case of ocean, what matters is mainly the temperature, and there are in case of sea maybe other things like the composition, like there is something called salinity, that is the amount of salt in water. Such things can make changes to the density of the water. We neglect all that. We assume that the density of what it's something, we assume it's always like this, around this value. Okay, 1025 kilogram per meter cube. That is what we assume the density of sea water to be always. Now, this next point I have already mentioned in marine hydrodynamics. We assume that it's an ideal fluid. Now, the meaning of an ideal fluid is that it doesn't have viscosity. We call it ideal fluid, sometimes we call it perfect fluid. All these definitions mean the same thing. It means that what you call as mu, I am sure you know this, mu equals 0. Okay, nu defined as mu by rho, mu also is 0. The kinematic viscosity, dynamic viscosity, all those are 0. So, you have an ideal fluid. Then you know what is surface tension. So, there is no surface tension, I have written it there. Then the last one is that the water surface is plane. At least in the beginning stages we make this assumption, that is what that means is that I have drawn a ship like this and I have drawn the load water line, right. I drew a load water line like this. We are going to assume it to be a plane always, horizontal. Okay, means it can really be like this and all, but such assumptions we do not make in this, at least in the beginning part of the course. There are studies later, but which can change this, but for the time being we do not have that. Okay. Now, we will go into the Archimedes principle, which you are sure to know. That is, when you immerse a body in water, let us assume that a part of it is immersed in water, or maybe the whole of it, it does not matter. It says that the principle says that the volume of water displaced is there is an upward force on the body which is equal to the weight of the liquid displaced. So, partly or immersed is buoyed up by a force equal to the weight of the liquid displaced by the object. That is what this figure shows you. You can see that initially the balance is showing 7 pounds. Okay. The balance is showing the weight of that bar, which is 7 pounds. Now, it is put into water. Now, there is some water has been displaced, as you can see the other bowl has collected some water. So, some weight of water has been displaced, mass of water, let us call it, weight or mass of water has been displaced to the other bowl. It is 3 pound of water. Now, that same amount of force is supposed to be, it is acting on this bar from bottom to top, from below to up. It is known as the buoyant force or buoyancy force. I think this. Okay. That is this name is, you will know it, but still it is very important. It is known as the buoyancy force or buoyant force. So, what you see is that the 3 pound is acting, and out of that 7, 3 pound has gone and the weight is showing only 4 pounds as you expect. So, this is the very basic concept of Archimedes principle. Then let us do some of the derivations in this book. Now, let us suppose that, let me keep it here. Okay, you cannot read it, but it is like this. There is a, I cannot, it is easier to see this than to draw it. So, you see this block, okay. There is a block, okay, it is clear in that. There is a block here, and this is the water plane, it is a horizontal plane. Now, let us divide this block into, different phases of the block into different names. The top one is 1, the bottom one is 2, and 2, this is 3, okay, this is 3, this is 4, 5, 6. So, it is divided like this. So, it is like this up to 6. Okay. So, just remember what the phases are. Now, let us take the phase 4. This is the top view. This is the top view. You are looking from the top. So, obviously, this side is the phase 4, means this one, like this is 4, this is 3, this is 6, and that is 5. Okay. And the top one, this is 1. So, this, let us call it the distance as L, this as B. So, when you have the block like this, one of them is L, this is B, and this length Z, it keeps increasing Z, whatever is the total, the draft is given to be T. Draft, again I have defined, is the region below water. Okay. Okay. Now, once you have this in mind, I am not going to draw it again. Phase on the force on the fourth phase, if you remember the fourth phase, it is, if I had it like this, this side was 4. Okay. This side was 4. Now, the force on the phase 4 is given by L into, now it is like this, that is, this is the block. Okay, let me, this is the whole block. Has it gone outside? No. This is the whole block, and let us say that the water plane is here, water line is here. This is how you write, okay, WL, water line is here. And now, you know that the pressure at any depth is given by rho g h, okay, that is known. We will write it as gamma. Gamma is the specific gravity, which is rho into g. Rho into g we write as gamma. So, gamma z rather, this is z. Okay. So, gamma z is the pressure at any point. Now, how will we get the total force on this? By integrating the whole thing, you will get the whole force. So, that is what we are doing here, L into gamma into d, gamma into z. Gamma z will give you at the pressure at each depth, L into dz will give you the area of that section, and the integral of that will give you the total force on F4, the total force on the phase 4, that is F4, plus of course the atmospheric pressure. Now, the atmospheric pressure is acting on L into T, L into T. Okay. Then that is F4. Now, similarly, force on the side 6 is this, I think this is 6, this is 6, this one. Similarly, it will be minus L into gamma z dz. Why is it minus? Because this force is acting like this force is acting like this in opposite direction, plus atmospheric pressure minus P0 into LT. Then now, as you can see, what will happen, F4 and F6 are cancelling each other. Okay. That is obviously true, because just because you put a block there, it will not move to this side or this side, it can only move up or down, which shows that the forces must be balancing on the two directions. So, obviously, F4 and F6 will cancel each other, we are just showing it mathematically. Then of course, there is another way to do it in case you do not want to do it in an integral fashion. This is of course the easiest and the most correct. Means you can look at force, I will just do this as well since they have done it here. The force can also be written as, there is another way to say this, force is also, now you have a pressure, we have seen a triangle of pressure starting from 0 at the, or atmospheric pressure at the top, it goes down to some maximum value. Now, if you take the area of the triangle, area of that triangle is a triangle of one side is pressure, okay, and the other side is a height. You know that the area of a curve, just like that, this will give the force, it will give pressure into height. Okay, you understand what I am saying? I think if you that is the area of this triangle will actually give you the force. Okay. So, what is the area of the triangle? Area of the triangle is equal to half T. Half T is the average draft, average of this, okay, half T into gamma T. It is like half base into altitude. It is just half base into altitude. This, what is the, let's like this. This is the area of the triangle. This is half, of course, and base and altitude. Base is the pressure at the bottom, which is gamma into T, where T is the draft, and this is the base, and this half base and altitude is T. Okay. You have got the area of the triangle, which will give you the area of the pressure distance. What will give you the area of the pressure distance is always the force. Okay. So, that gives you the net force. We are using the concept that area is actually equal to integral y dx. For you have done that, in area is integral y dx. So, that will give you the force. So, in this way you are getting the same thing. You will end up getting F4 equals L into half gamma T square plus, of course, atmospheric pressure you have to add. And with the same logic, you will get F6 to be the same as last time, the negative of this. So, when you do F4 plus F6, you again come to 0. Again, just remember one of these derivations, means just remember the first one. All you need to do is you just integrate the pressure over that depth, you get the force. So, you get F4, and in the other case you get F6 in the opposite direction as F4. Okay. Then this is roughly, now let us find out the difference between F1 and F2. That is, actually this is not our purpose, this is just to show something, but our purpose is to find out F1 is, as I have shown here, this is 1 and this is at the bottom is 2. Okay. So, at this bottom is 2 and this is 1. So, F1 minus F2 will actually give you the net force that is acting in the vertical direction. That is the purpose of our work, and that will give you the Archimedes principle, or that will give you the buoyancy force. That is what you want to find out. Now, F1 is very easy. It is the force acting at the surface. What is it? It is the atmospheric pressure. Okay. Let us give it in one direction. It is acting like this, down, minus P0 LB. Now, L is this distance, B is this distance, that L into B will give you this area, pressure is acting on that area, pressure into area is giving you the force in vertically down. Now, the force here will act vertically up, that will be given by F2 is equal to the same force, it is P0 LB plus gamma into LBT. Gamma into T will give you one pressure, and into L into B will give you the force. Okay. So, this additional component has come. This is the difference between the forces. So, gamma LBT is the additional force, or this is known as the buoyant force or buoyancy force. Actually, this is equal to gamma into, gamma is the specific gravity of water. Remember, it is not of the solid, it is that of the water. Okay. And LBT is the volume immersed. So, what you have is the upward force, the buoyancy force is equal to, if you want, I can write it in a term you are more familiar with, rho g into, which is actually what we are calling as gamma, into volume immersed, not the whole volume of the body, it is a volume immersed, which is LBT, not LBD. Okay. D is the depth, the whole thing, T is just the region under. So, LBT. So, this is what is known as the buoyancy force. This is the force that is produced due to the body immersed in the fluid. Okay. Now, there is a general derivation for this. Now, consider a coordinate system like this. Okay, let me just show this picture, that is easier than drawing it. Okay. Now, you see here a picture. Okay. Now, what you it's like the horizontal. Okay. Now, you have this coordinate system x, y, z. Okay. Now, suppose there is a body like this, it is a whole body and an irregular body. Let us assume that this body is given by these following equations. The top, this middle is where the water line is. Okay. This line you see here, okay. This is the middle, that is where the water line is lying, water plane. So, it is a plane, so it is a water plane. So, it is there. Now, the region above this surface is given by the equation z equals f1 of xy. You see, this region is given by the equation z equals f1 of xy. This region below is given by the equation z equals f2 of xy. So, two equations describe the surface of the sphere, surface of this, not sphere, this body. Okay, now, I will not draw this. Now, let us consider a small element on the sphere like this. Okay. We are considering a small element dA on this sphere and P is the pressure acting on that surface. You see here, the P is the pressure acting, P into dA will give you the force acting on that surface, on that small surface, that will give you dF. And if you want to get a force, the vertical component of the force means the z component, you will have to multiply it with the respective angle. Okay. This angle, the angle that it makes with the z axis will give you the component of the force along the vertical direction. So, once you know that, I will take this off and okay. So, okay, and one more thing is this surface is known as S1. Okay. The top part is known as S1 and the bottom surface we call it as S2, two surfaces. Now, the top surface S1 is therefore given by z equals f1 of x and y, and S2 surface is given by z equals f2 of x and y. Now, the force on element dA, I have already shown you what is dA, which is a point on S1 is given by P dA, this is dF. Now, as you know, this force will be directed along the normal always, means normal to the surface. Okay. The force will always be along the normal to the surface and therefore, to get the component along the vertical you will need to multiply it with the corresponding angle. Now, the vertical component of the force will therefore be given by, now pressure is, what is pressure? Pressure is equal to gamma rho g h, rho g z, in our case z, okay, rho g z, which is gamma z. Now, z is what in the top surface? F1 of x y, we have already defined that. So, gamma into F1 of x y will give you the pressure at the surface into dA will give you the force, this is that dF. Is it clear or should I repeat something? Okay. All right. So, what we have here is, I have shown you what is P dA. Now, to get that P is rho g h, rho g is gamma, h is z and z is given by f1 of x y for the surface S1. Therefore, I write dF as gamma f1 of x y dA. Now, if I multiply it with the angle that cos of the angle between n and z, n is the normal. So, this force is actually the force along the normal. If the surface is like this, it is a normal to, if this is dA, okay, this is the direction of normal and the force is directed along that. Now, I want the component of this force in the vertical. So, I multiply it with the cos of the angle between the normal and the vertical. So, that is what this thing represents, cos of n and z. So, this represents the vertical component of the force. As I have told you before, we want the vertical component of force because we are always talking about the buoyancy force. Okay. Now, this is over a small element dA. Now, let us suppose we want the whole area of S1, we integrate this. Okay. Okay, comes like this. Now, there is another way to write this. Look at this, instead of multiplying with the cos with this expression, means this cos can be multiplied with this. Now, this cos can be multiplied with dA. If you multiply dA with cos, what will you get? Yes, what will it be? It is dx into dy. Just think over it. It is dx into dy because it, right? Okay. So, this will be basically we had that area like this. Okay. That area is like this, dx dy is like this. This is dx dy because this is z, this is x, probably this is y. Okay. Or this is x and this is y. At any rate, this will give you the xy plane. So, dA into its component will give you dx dy. This dA is in this direction, it is in this direction. You actually tilt it in this, you get it the dx dy. Okay. So, this will give you gamma f1 of xy dx dy. So, this let it be here. Now, what else do we have in this? We have this bottom half of the body. Now, in that bottom half of the body, we have the surface S2. Now, I am not going to repeat the whole process. It is exactly the same except that the sign will be different. That is down, this is up. Okay. The normal will be in an opposite direction. In that case, the normal will be in one direction in z. In the other case, the normal will be in the opposite direction of z, because the body is like this, the body is like this. Here the normal will be like this, here the normal will be like this. Okay. Always directed out away from the body. That is how the normal is defined. So, on the surface S2, you will have the force acting will be gamma into on the surface S2 F2 of xy dx dy. Okay, it will reduce to this. Now, so what is the net force acting? F is equal to gamma into F1 of xy minus F2 of xy dx dy. Now, what exactly is this representing? The integral, that is all, that is very simple. So, this represents the volume of the body, because this is representing, it is actually z dx dy, z dx dy is the volume of the body. So, this is representing gamma into V, volume submerged. Okay. This, in this case, the whole body was submerged. So, we are talking about the volume submerged. So, this is, that is what it is, that is what we have seen, gamma into, we have seen the previous definition, gamma into volume submerged. So, specific gravity into volume submerged. This is a very rigorous or very exhaustive like proper mathematical derivation for the Archimedes principle, Archimedes buoyancy force. So, this is the final thing that you carry away from this class, that is it is gamma or rho g into V. This gives you, again I tell you, V is the volume immersed, not the total volume of the body, and rho is the density of water, not the density of the body. So, once you have those two clear, rho g into V will give you the weight of the buoyancy force, or it is if the body is remaining like that, that means that the weight is balanced by the buoyancy force, that means that this is the weight of the body, weight of the body is balanced by that. Okay. Then now, okay, that is actually the next part. Yeah.
So, when computing the net force, what happened to the normal components?
Normal components.
Initially, before when we wrote force, we wrote it as dF into cos nz.
Yes.
So, when
that gives you the component of the force in the vertical direction. See, this is, if this is the, let me see, suppose this is your body, let us assume this is the surface of the body, the normal is like this. Okay. So, what I did was, I am only interested in finding out what is happening in the vertical. What happens in the horizontal, we are not bothered so much, that is a different thing. That is like propulsion, thrust and all that, that is a different thing. What happens in the horizontal, vertical only we are talking about as Archimedes principle. So, when you have a normal like this, normal means normal to the body, not vertical. Okay. Get that clear. Now, normal is like this, I am just finding, so when I multiply this normal with the cos as I have done there, it will give you the component in the vertical direction. So, you get the vertical component of force. So, what I did was I subtracted the vertical component of force from the top side minus the vertical component of the force from the bottom side, that will give you the net vertical component of force due to the pressure. That is the vertical component of the force. What you are asking is horizontal component, forget that we are not bothered about it for the time being. Okay. Okay. Okay, then now we have to find out, okay, this is the equilibrium principle, that is, it says that the weight of the liquid displaced is equal to the weight of the body for the body to float in equilibrium. Okay. The condition for equilibrium, actually this is a very important term, equilibrium, which is what we are more or less concerned with in this whole course, different types of equilibrium in fact. Even stability is about equilibrium only, but stable equilibrium, neutral equilibrium, unstable equilibrium, there are different 3 types of equilibriums, we will come to that. Before that, the basic condition of equilibrium is that that weight displaced or some volume that we have, this is what this picture in fact explains more than what I can do, like the weight displaced is equal to the amount of force that is acting upwards, and that will balance the force, balance the weight of the body. Okay. So, the weight of the body is balanced by that upward force if it is remaining in equilibrium. If it is remaining in equilibrium, the weight of the body will be balanced by that buoyancy force, and that buoyancy force you can find out, it is the equal to the mass of buoyancy force is equal to the weight of the liquid displaced. This is equal to this force, and this balances the weight of the body. That is the thing. Okay. Okay, then let us suppose that W is the weight of the body, it is balanced by the delta. Delta is equal to gamma into del. Okay, gamma is rho into G, so it's okay. So, W is the weight of the body. What again, if you look at this picture, you see, let us suppose that weight of that is, the weight of that is W. W is equal to delta is gamma, del is again submerged volume. Okay, submerged volume into gamma will give you the weight of the liquid displaced. It is equal to del, it is written as delta, I mean this is del, this inverted one is del, this one is delta, delta is equal to gamma into del, it is actually the weight of the liquid displaced, it is the buoyancy force, it balances the weight of the body, that is what this shows, this is the weight of the body. Okay. Now, we will write it like this, gamma into del equals W. Now, we just write it in a, we are now looking at in an engineering point of view. Till now we are doing the mathematics of it and physics. From an engineering point of view, this is of course the same thing. CB is the block coefficient, CB into LBT will give you del if you look at the definition. So, gamma into that is equal to sigma Wi. What it represents is, as far as a ship is concerned, it is not a whole one thing, means Wi, all right. Now, ship itself we define it in different, there are different weights associated with a ship. One of them you call it as the light weight of the ship. Now, by light weight of the ship you mean that suppose you remove everything from the ship, not everything, suppose you remove all the cargo, all the people, things like water, oil, engine, all those things you remove from the ship, you are left with the bare structure of the ship and a couple of things like pipes probably, some things are remaining. Now, if you consider all those, that is known as a light ship, okay, and to that you add different weights like cargo weight and other weights you add to the ship, and so what you have here is actually the sum of the weights, total weights of the ship. So, this is the formula for as far as naval architecture is concerned. The total weight of the ship is given by gamma into CB into LBT. And of course, you can see this, if I replace this gamma with rho, okay, you can do that. If you replace this gamma with rho, you immediately replace this with m, right. If I put gamma there, you have W weight, if you have rho there, you have m there. Okay. Now, actually we will go into the next thing. Now, this small part which I am going to take now, I suggest that you listen carefully, because this is the one of the very important things which if you do not understand the rest of your lectures you will not understand. That is about the tilting of body. We are now going to talk about, I have already told you, if you have a ship like this, if it tilts like this, it is known as heeling. Okay. So, from now for a couple of lectures now, we will be dealing only with heeling. We will not be doing anything with trimming, okay, nothing, we will be only dealing with heeling. So, we always take a section like this, we always look at it like this. As you can see, this is a section, this picture is showing a, this picture is means okay, that it was showing a, it's like this, yeah, this one. As you can see, this picture is showing a section of the ship, okay. Now, this ship is tilting, I will explain, that is what I am saying, what I told was most important, you have to listen what these lines mean, WL and W1 L1 or WL1, then the two lines I will explain very clearly now, that is very important. Okay. Now, before that, suppose you have this body, there are 2 points that are important. In the beginning at least, there are 2 points that are very important. One is known as the center of gravity and 2 is known as the center of buoyancy. Now, you know what is the center of gravity? It means that suppose you have different masses on the body, let us assume that there is a point. If you assume the whole mass to be concentrated at a point, you call that, it is like the centroid of that mass, okay, that is what it is, the center of gravity, either mass or weight, okay, centroid of the mass or the centroid of the weight is called center of gravity. Now, just like that you have an immersed portion of the hull, right, there is a volume there. Now, the centroid of that volume is called as the center of buoyancy, okay. Centroid of the immersed volume, not the whole volume. known as the center of buoyancy, and this is of course the centroid of the mass. It is not nothing to do with submerged body, that center of gravity means it has nothing to do with the submerged volume or the submerged, it is the total mass, it is the total weight. Okay, there is nothing there about. So, the center of gravity could probably be outside the volume, outside the submerged part. If you have, means suppose you have a body that is half submerged and half outside, suppose part of the weight is out here and part of the weight is here. Let us suppose that more weight is here than more weight here, obviously the center of gravity will be here, means it will be in this volume, in this region, but center of buoyancy is always inside. We are considering only the inside part. So, let us draw this. You have these two figures, as this figure you have this center of gravity is always denoted as G. In our calculations you will see it put as G, and center of buoyancy is always put as B. These are all fixed notations. So, first in this case you are having a having a rectangular body which is immersed up to this point, this is WL, up to this point it is immersed in water, and it is floating upright. Therefore, this is G, here the weight of the body is acting delta. Now, the buoyancy force now this centroid of the volume is where the buoyancy force will act, okay, because you saw that the buoyancy force is to do with volume only, volume of the submerged portion. So, you can assume the whole thing to act at the center of buoyancy. It is acting all over, but you can assume it to be acting at the center of buoyancy, the whole of that. So, here it is acting at B. Now, this is in equilibrium. So, at G delta is acting down, at B delta is acting up. The same weight is acting up and down, it is in balance and it is staying in equilibrium. And it is in equilibrium, that implies one more thing, this will be in one straight line. Okay. Let us see what will happen otherwise. Now, suppose that due to some reason the G is shifted here. One possibility is that lot of weight on the left side, I move it to the right side, as a result of which the G moved here. From the initial G, let us say this is G1, it is moved to G1, B is again here. Okay. Now, delta acts here and this acts here. In this case, there is no imbalance of force, force is balanced, delta is acting up, delta is acting, but there is a moment coming up. Okay. Here there is because you can see one force is acting like this, one force is acting like this, there is a moment like this, it is causing the whole thing to rotate. So, it will cause it to rotate like this. Now, when it rotates, what will happen? What will happen is that more volume will come on the right side, this will rotate like this. Okay. So, this will go up, this will come down, more volume will come on the right side. Now, the center of buoyancy will slowly start shifting to the right again, because more volume is on the right side. Center of buoyancy is again to do with the immersed volume. So, it slowly starts shifting to the right. Therefore, it keeps going and it will finally come to a state such that the buoyancy force, the center of buoyancy and the center of gravity are again in a straight line. Okay. It will come to such a point and it will stop there. Then there is no moment acting and it is at stable equilibrium, it is at equilibrium at least. So, it will just keep going and so, it is tilted such that B has now, this was the initial B has now shifted to this point B1, G was initially here somewhere and G was shifted to G1. It has finally come such that, okay, its G is here and it has come such that it is in the straight line. Okay, this is the straight line. Now, it is in equilibrium again, forces are balanced, moment is balanced. Okay. Now, comes one of the what I am talking about, there is another way to look at it. Now, as you saw here, in this case I drew this figure, you saw this body was drawn as straight right, means upright. In this case I have drawn the body as a little tilted. Now, instead of doing this all the time, so if you want to really study that, you have to do it. If you want to study how the buoyancy force moves, you have to keep tilting the body and you have to draw it. An easier way to do this is, instead of tilting the body like this in the drawing, you say that the water line is tilted like this. Okay, means you have initially like this. Actually the body has tilted in this direction. Okay, body has tilted like this, but instead of doing that, we assume that this water line has tilted like this, and I draw it like this, W1 L1. This concept you have to remember. Okay, this is how, because you will see the water lines in different directions, you have to know that when a water line is drawn like this, it means that the body is tilted like this in the opposite direction. Okay. So, this same figure that I have drawn there is usually drawn in naval architecture. You will never see a body tilted in naval architecture, you will see only the water line tilted, okay, in the literature. So, it will be drawn like this. This is a section of a ship, and this is W0 L0. W0 L0 of course represents the initial water line. Then now what have we done? The ship, we have in that drawing, that ship has tilted like this. Instead of that, the water line has tilted to this new point. So, from now on, never get confused when you see a tilted water line. Actually the important thing is, what you have to remember is, this tilted water line does not imply that the water line has tilted like this. Some people have asked me many times, so the water line is no longer horizontal now. That is what this looks like. You look at this, this looks to me, this figure seems to, this is obviously horizontal, W0 L0 is horizontal, and there is no confusion there. But W1 L1 does not seem horizontal, it is not horizontal. So how is it, what does it imply? The water line is not horizontal. It is not that is not the meaning at all. It just means that the body has tilted like this. Okay. W1 L1, I repeat again, is exactly horizontal, and I will tell you what I mean. Now, initially G was here and B0 was here, or let us call it G0 and B0. This B0 is acting, delta is acting up, G, this is acting down. Now, because of this tilting of the body, G is now here G1 and B is now here B1. Okay. Now, tell me what will be the direction of delta in G1? It will be perpendicular to W1 L1, exactly. It will be perpendicular to, not vertical now, because that is vertical, that perpendicular to W1 L1 is vertical, this is vertical. So, this is the direction of delta, and similarly this is delta acting here. Okay. I mean, I think you have got the concept. So, this is one of the most confusing probably things in in this course. Many people, I am sure many people will again come and ask me, but in the exam you see this written, this confusion you will see sometimes, this word. So, the idea is that this W1 L1 is always horizontal, and this from this G, that even though the line looks not vertical, it is actually a vertical. So, this line from G1 acting down to delta is actually a vertical. Okay. So, this is the vertical in this diagram. Okay. Now, so that is what this figure is showing. Okay. That is, you are seeing here, okay, this WL is the initial position of the water line, and the body has tilted to the right side, as a result of which WL1 has moved up, not to the right, it has moved up in the opposite direction. Now, this W1, even this WL was horizontal, this W1 L1 or WL1 is also horizontal, and so some new region, this wedge, they have said it has gone inside, new wedge means a small section, a section of volume has gone inside the water now, and a same section of volume has actually come out of the water on the other side. Okay. All right, then now there are three types of equilibrium I have told you. Okay, this is different. Equilibrium of course means a body is remaining at rest, and there are three types of equilibrium associated with a body. The first one is stable equilibrium. I will just write the names here. So, there are three types of equilibrium: stable, unstable and neutral equilibrium. Now, the stable equilibrium means the body is in equilibrium. Now, I give a small perturbation to it, it goes like this. I leave the perturbation, it comes back to the original position. Okay. That is the meaning of stable equilibrium. So, again the body is in equilibrium, I give a small tilt to it or a small perturbation to it, it goes away from its position of equilibrium and it comes back to the position is known as stable equilibrium. Unstable equilibrium means it is remaining at rest, it is in equilibrium, the moment I give a perturbation it just capsizes or it goes completely out. Okay, that is known as an unstable equilibrium, the opposite of the stable. The third one in middle in the between the two is known as neutral equilibrium. It's in remaining in equilibrium. I give a tilt, it goes and stays there. It doesn't come back, it just stays there. I give a tilt more, it might tilt a little further, and possible if you tilt it further, it might capsize. So, at that point of neutral equilibrium, it is just between the stable and unstable. So, we can actually look at it the stable equilibrium. The stable equilibrium we can look at it in a in this way, that is, there is a body like this. This is let us say T, this draft is T and L into B. Now, let us suppose you push it down a little further, from here I push it down by an amount delta T. Okay. Now, this is L into B, okay, L into B. You can see that the initial buoyancy force was LBT, something proportional, gamma into LBT, of course proportional to LBT, okay, and or I will just write it itself, gamma into LBT. Now, when I pushed it down a little like this, an additional amount delta T has come into the water, and there is an additional force given by gamma in additional this is the initial buoyancy force, initial buoyancy force. Now, means at a later time after I push it, the buoyancy force is given by LB T plus delta T, right. So, obviously what happens, there is an additional force, I just pushed it down and I have left it. Now, there is an additional force acting, it is slowly pushing it up. I mean initially what was it, weight was balanced by gamma LBT, so it was remaining. Now, there is this gamma LB delta T additional force acting up, so it is slowly bringing it back to the original position. So, that is the meaning of stable equilibrium. So, we are I think we will stop this lecture here. Okay.